On the project today. So we have a project on these four problems. Let me first discuss the marks distribution. So we had decided in the beginning that we will have assignments plus quizzes will have 40% marks, and right, and mid-sem exam 25%, end-sem exam 35%. This was our initial earlier discussion. So the breakdown is something like this. You have submitted 3 assignments in full, 4th assignment partially, and the 4th assignment some part is remaining. For that, the deadline will be coming Monday, means during the vacation. So you can submit it by Monday 2 p.m. Monday 2 p.m. and that will be online because you will be at home most probably. So this is now the codes are remaining, right? You already have submitted the write-up. So now, if you want to submit the codes and submit the write-up again, that's fine. Write-up means the updated version of the write-up. That is the 4th assignment is for 8 marks because there is a coding component also here. Total 24% marks. There are 2 quizzes. One quiz for 8% has happened already in the past. One more quiz will be there, and that will happen after the mid-sem break, maybe in the first week of November. So mostly it will be either on Monday or Wednesday or Thursday. And then mid-sem exam is already done, 25%, project end-sem 35%. Now there is a project which is for extra credits. So what is the advantage? You can use this project to replace your mid-sem credits. For example, your mid-sem you scored less. So if you do well in the project, you can use these marks to kind of compensate for that performance, right? I'm doing this because some students, they approached me saying that they want to do well, but somehow they did not get good marks in mid-sem exams. So I said, okay, then do well in the project and we can use. Is that all right?
So the summation of assignments not coming up to 24.
Is not?
Coming up to 24.
23, huh? 23. Okay. We can make some adjustments here, maybe 7, then this is 22, and this is 9% each. All right? All right? Okay. Fine. This project will be 20%. This is so far extra credits, and you can use it to replace the mid-sem. Okay, but this project will be very useful because you will learn the real stuff here. All the previous things was theory, but now we are going to do some real stuff hands-on. Okay, let me now come to the project. The project has 4 problems: tonic estimation, melody estimation, stroke detection, and singer diarization. So the first problem is, the bigger picture is like this. So you have the timeline is like this. So data collection and manual annotation, this will be done by 30th of October. 30th of October is immediately after the mid-sem break, right? That is Monday after the mid-sem break. So by that date, if you are ready with your data, and then you have to submit your data and the annotations by 30th of October, right? And then you have 1 more week to submit your method. So you will submit your methods by 6th of November, and on 9th of November you will have final presentations, which will be in class. So I look forward to learning from you in those presentations. Any questions?
Can the project be used to replace the assignments or the prelims? Like, is it a
Um, I think it can be treated as a complete bonus, so you can use it to compensate wherever missed you missed out. Maybe mid-sem or assignments. Do you want to make it mid-sem or assignments? Mid-sem and assignments, not quiz, huh? Everything. But then end-sem also is covered, huh? Huh? Everything? Be just mid-sem and assignments. Huh? Mid-sem and assignments, not quizzes. All right? This will be a little difficult. How do we actually do it? Okay, but not end-sem. Maybe. All right, this is fine. Now let's come to the project. Let's do some real stuff now. The first problem is tonic estimation from drone. So every problem you can see as having 3 steps. One step is data preparation. Second, data preparation means data collection first. Second step is data annotation, which means you have to understand the problem and you should know how to do it manually at least. Like machine learning is useful for scaling up things, but first you should know how to do it manually so that you can make ways to scale up things, right? So this is the first part. You have to do data collection, then data annotation, and then the next will be using machine learning or signal processing for solving the problem. So let's take the first problem, which is tonic estimation from drone, basically from any audio file, and you can use the drone part to detect the tonic, to estimate the tonic. Okay, let's first see how do we collect the data. How will you collect data for this problem? How will you collect data for this problem? Use your laptop, do surfing, find out how will you find data for this problem. All of you understand the meaning of this problem? I think last session was on music, and we also showed you how do you do music analysis. The question is tonic estimation. How will you collect data for this problem?
Data from drone.
Means you can use drone to estimate the tonic.
Drone to data, record audio.
Yeah. Indian classical music. So I will, like a typical audio will sound like this. Yeah, you can also get ready-made data sets.
That the drone is in the background of the singer, or drone is recording the audio?
Okay. I think there is a
musical drone.
Yeah, it is. So drone has different meanings. So in the before this modern era, drone meant a bumblebee, a bee who is flying, and it will make sound like that was called a drone. But then when the musical instruments, when we talk about musical instruments, then drone is a musical instrument. It's called tanpura, which will play a sound, which will also sound like but it's the music. It will give the musical notes. And then in the modern era, when there are flying machines, and those small flying machines, they also make some sound like this. They are also called drones. So we are referring to the musical drone here. Yeah. How will you collect data for this problem? So Sanjeet suggested that we can just download an existing data set. That is the easiest thing to do, but not the most educationally enriching experience. So how else will you get the data? Yes? Yeah, live classical performances, where will you get them? YouTube. Yeah, you can download data from YouTube. Very good. Okay, I'll make your notes. Yes? Yeah, you can get it from YouTube or any other musical recordings. There are so many sources of music recordings. Spotify, Pandora, Savan, Geo Savan. What else? Huh? Yes, easy to download from YouTube. Okay. Then next step is, how will you annotate the data? That is not easy. How will you annotate the data? Pitch estimation. Okay. There is a simpler way to get this data.
Hindustani, Alankar, and Raghav data set.
Yeah. So that is what Sanjeet also suggested, that there are existing data sets which you can make use of. Okay, now I'm just going to play one app which I have. It plays the drone instrument for you. And you can set the frequency also. Like this is C4, C sharp 4, D4, D sharp 4. So basically you can use apps, different kinds of apps, because one app will give one kind of sound, other app will give some other kind of sound. You can use different apps also to record the data. And then there are also on YouTube or on other sources on internet, there are apps or tools to play drone instruments. Let's say on YouTube, if you say, I want Tanpura on scale C scale Tanpura, it will have a long audio recording which is playing the same Tanpura. Or if you even ask Alexa play Tanpura at scale 4 D, it will also play. So Alexa also knows that. So it's a very good source also. So I will say, yes. You can add them. You can add instruments on top of it. Yes. There are many apps which you can use. Okay, how will you annotate the data? So let's see, can we annotate it manually? Let's see if we can do that. I will just open an audio recording on Prat. This is All India Radio. So this is an audio file which I just got from YouTube. It's from All India Radio. All India Radio has lots of music data, and many of their files are available on YouTube. Like this file is from 1986, very old file, but it has very good audio quality also. So this is the drone part I can see. Let's zoom into it. Can you tell me what is the, okay, no, I will not do it. You should do it. How will you do it? Huh? Can you open Prat on your machine and tell me what is the drone frequency here? How will I share this file with you? Shared folder. Okay, I will put it in the shared folder. Good suggestion. Okay, so when I recorded this audio file, so how I recorded it is I just played YouTube and I recorded it on my device itself, my laptop itself, and the format was something else. Now there is a tool on in Bash. This tool is called SOX. It's a very good tool to manipulate audio files. If you want to, what do you say? Convert the sampling rate, change the sampling rate of audio file. It's a very simple command. Just in one line you can change it. If you want to change the format of the file, let's say from MP3 to WAV or it's something, you can use SOX. If you want to change the, what else you want to change? The timing, let's say the file is, I said something in 1 second and you want to elongate it to 2 seconds. Let's say I said music. You make it double length means music. Slow it down, right, and made it longer without changing the pitch, without changing my voice quality as much as possible. SOX is a very good tool to do that also. Like that, SOX is a very good tool. Just a simple command SOX and then everything you can put. Oh no. How do I change the resolution? Bigger, okay. Okay, but to convert, I had some format MP4. For that, SOX did not work. So there is another tool called FFmpeg, which worked. So I use this command FFmpeg I minus I MP4 file and then WAV file. So it converted MP4 into WAV. Anyways, this was just a small useful tip. Okay, how will you estimate the pitch? Tell me I have shared the file on the project thing. Tell me what is the drone frequency or the tonic of this file. Tell it in hertz only, no need to convert to MIDI number or that A4 A sharp notation, MIDI notation. Because in Indian music, you can have any continuous value. Got it? Shared folder. And then there's a folder inside called project, in which there is a file called ramjog.wave. Okay, tell me the drone frequency. You can pair up with it. Okay. Did you get it? Anybody? Any success? What are you doing? No progress. Yeah, yeah. You have to find out what frequencies, what window rate, etc. you will be using. That is totally your choice. Whatever helps you. What will you do? The chart has a kind of restriction that your window size has to be less than 10 seconds. Only then it will plot the spectrograms, etc. Done? 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 Not done? Not done? I have to zoom in so that we can show you this. So you have to zoom in, otherwise it will not show the spectrogram. You will zoom into a window length of less than 10 seconds. Why not this one? This one? Why? You have to justify your answer. Why is it an anomaly? How many of you are done? What's the answer? 470. 470. Okay. 470. What's your answer? 470. 470. What's the justification? Lower part is fine. What is it that is anomaly? Anomalous. Yeah, I think one mistake which I found most of the students doing is that their window size is so small. If your window size is very small, how will you capture the frequency resolution? Right? If your window size is very small, your frequency resolution is also very small. So you need a little longer window to increase the frequency resolution. Otherwise, you won't see the pitch patterns. So now tell me, what is the answer? 470? 470? Let's check. Okay, so what I am doing here is, first of all, I will zoom into the region which I know it is drawn. This is a drawn part. I will do the selection. The window size which I have chosen is 50 milliseconds. This is the window size I have chosen, 50 milliseconds here. And my view range is 75 hertz to 1000 hertz. That's my view range. So what I can see here is, I see multiple peaks. This is one peak, another peak, another peak, another peak. Which one should I choose? I will turn off the pitch setting because anyways pitch is not. Which one should I choose? This one, or this one? So this is 473 hertz. This one is 712 hertz. This one is 944 hertz. But then there are so many other peaks also. This is 348 hertz. Which one should I choose?
So they're all in the same, all the same, it's just a different scale. Because 470 was like 944.
But this is not same. 470 and this is 350.
350 probably maybe the fifth note in the scale.
Huh. Okay, good. Yeah. But I can also say that 350 is my base frequency and 470 is the fifth note. No?
Yes, it's like the fifth note on the scale, 350 hertz.
Huh, but I could also say that 350 is my base frequency and 470 is the fifth note. No?
No, I don't think that works. Because for 470 to 350, 470 is not 350, and 350 is fifth note.
How? Just check it.
Yeah, I know the scale.
Huh?
I know the scale, so I take the frequency range also.
Okay. There is a very good web page which can help you know certain things. For example, just a minute, I will show you. There is a web page called inspiredacoustics.com. It shows you the MIDI note number, anyways, this we have not discussed, the note names, and then this is the frequency, note names and frequency. So you can see here, when you are talking about, let's say 350 hertz, it is F4. When you are talking about 466, it is A sharp or B flat. Right? Okay. Okay, so let's find out. Yeah, I think what you suggested is a good way. Okay, so the drone, the Tanpura, it plays sa pa sa. It plays notes which are either sa or pa. Sometimes you can also tune your Tanpura to play sa ma sa, but mostly it plays sa pa sa. Let's zoom a bit more. Now you can see it has a repeating pattern. Let's find out from here what is the frequency of this pattern. Roughly this much. So 0.0216 milliseconds is the, this is the, go to Python. Okay, so tell me if the time period is 0.0216 seconds, what is the frequency in hertz? Oh, 010, I missed. No. This frequency is too low. It won't work. It is coming out to be 46 hertz. This is not one cycle. Yeah, Tanpura is difficult to know. Means if you see this one cycle is just 46 hertz frequency. This is not the fundamental frequency. Okay. Yeah, Tanpura is tricky. Yeah, this is the right fundamental frequency from here to here. But it's very difficult to know from the waveform. Yeah, but okay, thank you. I think that's a good way to measure the fundamental frequency, that you hear it and you see the. And if another way is, the one way is that you see the peaks in the spectrogram and then find out whether it is SAPA SA, and from there you can tell what is the SA frequency. So how I verified was something different. What I did is, okay, let me hear a little bit more. So if you have some musical knowledge, you can kind of conclude that this lady, the singer, is now settling to the SA frequency here. Right? So from here, because the singer's SA is very clear to determine. Tanpura is difficult, but singer's SA is very easy. So you can see clearly here, this is the fundamental frequency, 230 hertz. So the fundamental frequency of this singer is 230.8 hertz. Yeah, for drone. Yeah. So what is 230.8 hertz? 233.08. So A sharp. Her frequency is her note is A sharp. Tonic is A sharp at 230 hertz. But from Tanpura we got double of it, which is also fine because we want to know the scale actually. Okay, so this was my way to determine the SA. I looked at the. Okay, but now this is good to get the ground truth. But then again, you can train your machine to do the right kind of mapping, right? You can train your, let's say, treat it as a classification or a regression problem and get the answer with your machine learning approach. All right? All right? So manual way is clear. Now machine learning way you have to think of, because it's just a classification or regression problem. You may use CNNs, etc., to map your input to the right kind of output. You have to construct the output. How you want to construct that is totally up to you.
Can you explain again how did you decide this lady's voice?
Okay, good question. So if you look at the drone, then that part is clear, right? The drone part is clear. So for drone, it gave me this is the most prominent frequency. But then since you can see that this is 470, and then this is exactly double of it, 712. Double of 470 is how much? No, 800 something. Huh? 9. Oh, this one. This is the double frequency. Let's zoom out a bit. Spectrogram. Let's go to 5000 hertz. You can see here. So generally, this is how much? 4704. 4476. So I think because there are two notes playing sa and pa, so that's why you see a bit of confusion here. Yeah. Okay, now the question is, how do I determine the singer's F naught? for that you can see here this structure, that you have this frequency is 230, this is the double, this is f naught, this is 2 f naught, this is 3 f naught, 4 f naught, so on and so forth, right? See, it's very, it's changing so fast, the pitch contour. This is Indian music, the continuous transitions. With the next problem is melody estimation. Melody estimation means now you want to estimate the melody at all the points, like here, 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 etc., etc. So how will you determine the melody? Take a small frame and look at the periodic structure there, and from there you try to estimate the melody. So this is the manual way of doing it. Machine learning method, again, just design appropriate model and then train it and then test it. I will show you some difficult problems here. Let's say if you go to another recording. Okay, is it clear that how will you determine the melody of this song? Can you do it manually or in whatever way? Can you do it manually? Even if I zoom it, I will see very good structure in the waveform. Even the waveform is periodic. No. So you can see that this structure is repeating over and over again, right? This structure is repeating. So in temporal domain also you can find the melody, but in the spectral domain it is much easier, right? It still looks very noisy, but this one is very clear in spectral domain. Okay, any questions up till here? Any questions? Okay, now I will show you another spectrogram from same audio but little later, means it appears little later in the performance. So you can see that now it is very difficult to determine the melody from this piece, right? It's having so many variations. How will you determine melody now? How will you do that? Yeah, there are some tools, but I don't know how well they perform. Means generally they are not very perfect.
It actually isolates into 5 different tracks.
Yeah, you can try it on Indian classical music and see how it performs, but I'm very doubtful. Like, this is a very difficult piece of audio. I've shared this audio in the shared folder. You can try that app or that tool on this. You have tabla playing, you have singer singing, drone playing, even harmonium is playing. Now determining F naught becomes very difficult, but still in some places it is very clear. If I do the pitch estimation, it will be really a mess. You can see. Like here it is totally incorrect. Here it is, somewhere it is correct. In some places it is correct, but many places it is incorrect. Right? So it's not an easy problem. Okay, but you can see it manually. At least manually you can see that happen. Okay, what can you do? You can change the window size. If I make the window size let's say instead of 50 milliseconds, if I make it 80 milliseconds, then how will it look like? The frequency resolution has increased, but wherever there are transitions, there it has become very messy. And then you can make it shorter, let's say 30 milliseconds. Now you can see frequency resolution has become bad whenever there is flat note, but when there are transitions, there the frequency resolution is very good. Means there you can see the transitions very sharply, right? Very sharp transitions are visible. Here, for example, very sharp transitions are visible. Here, when here, right? Just notice this. If I make it 80, or let's say 50 also, you can see a change in these transitions, right? Transitions are lost. Did you see this portion? Here it is very blurry, right? But if I make the window shorter, okay, just focus on this region. Focus on this region. Here it is very blurry, right? But I am just reducing the window size to 30 milliseconds. See, it has become so clean, right? On the other hand, you see this flat note, this flat region where frequency is almost constant. Here you can see how the increasing window size helps. I am applying now. Just notice this region. Notice this region. See, it has become much more sharper. If I make it 80, then it will become even sharper. So you can play with the different window sizes also to know the right melody contour. So generally such recordings where there is a very fast variations, I think it's a good idea to use a mix of both windows. Right? You may plot different spectrograms and feed all of them into your melody estimation program if you're using a model, right? A convolutional model or something, right? Yeah. So I have shared this is one paper. It's so this tonic estimation is, not many people have worked on this problem yet, but a few works are available. This is one of them. Because it's a problem in Indian music, and mostly people work on Western music, means because within India, very few labs are working on Indian classical music. I know only 3 labs other than IIT Kanpur. One is in Kharagpur, one is in Madras, one is in Bombay. That's it. And just one research group in every IIT, those 3 IITs. Okay, so can we get data for melody estimation? Yeah, how do we get data? How do you get data for melody estimation? Yes. Data preparation. How will you do data preparation? Okay, so any ideas? How do you prepare data for melody estimation? Any music?
Like any music with just the vocals.
Yeah, just the vocals, yeah.
YouTube files which have only vocals.
Yeah.
Use them to be on track to get the pitches and then.
So such audio files are called monophonic audio. Polyphonic means many instruments are playing together. Monophonic means only single instrument or vocal is playing. So generally, the algorithms like Pratt or other algorithms, they are very good for monophonic audio. But for polyphonic audio, their performance degrades because of the reasons you saw, right? Even visually inspecting them becomes so difficult. I showed you 2 recordings. The one was where the singer was singing alone. There you could see the patterns are so clearly visible. Even Pratt did very well in estimating those pitch contours. But the moment you saw the other thing, where other instruments are also playing, melody estimation becomes worse. So what is the trick? You take monophonic audio recordings, estimate pitch there, and where you know that okay, it's a good pitch estimate, and then you add other instruments later. Right now you know the ground truth because you know the monophonic pitch contour, and then you can use that mixed data to train your models. Right? That is the common trick.
Sir, can we train a audio source separation and then
Yeah, audio source separation in itself is a very difficult problem. It's not.
When it could solve all of these at once.
Yeah, the question is that that single problem itself is so difficult that it may not be able to solve these problems very effectively because the errors will accumulate now. Huh?
Source separation can never be perfect.
Yeah, source separation is a very difficult problem. It's a very difficult problem. Compared to these problems, that is much more difficult. But yeah, you can try that way if you want to try. That's totally fine. Okay, how else can you get the data? There are some existing data sets also which you can definitely use. They are mostly for Western music, but there are a few on Indian music also. And then how will you annotate them? Either you use Prat for monophonic, let's say Prat does not do very good job, but you want to manually annotate the data, or Prat does some mistakes and you want to manually annotate the data. How will you do that? You have seen many examples, right? When she was singing, sometimes Prat made a mistake. But then you could very obviously tell, okay, this is an obvious mistake. I want the pitch contour to be here, not here. Right? How will you manually correct the Prat data? That is very difficult. For that, there are hardly any tools, but I know one tool which can do that. It's called Tony. T-O-N-Y or T-N-I? T-O-N-I, I don't know. But anyways, it is Tony. It's called Tony. This tool can, you can kind of, it will do some automatic pitch estimation, and wherever it has a mistake, you can select that region and you can move it, and you can correct those things manually. Auto-tuning. Auto-tuner. I don't know. Tony is... No. You're not correcting the audio. You're correcting just the annotation. That line, the pitch contour. You're changing the pitch contour, not the audio.
In melody estimation, we just want to know the pitch of the singer that is singing.
Yes. You want to estimate the pitch of the singer. What notes the singer is singing, or what frequencies the singer is singing. Okay. And for modeling, you can treat it as a regression problem, because in Indian classical music, it could be any continuous value, right? You could treat it as a regression problem.
So we are only focusing on monophonic sound.
No. I'm saying monophonic is for data preparation, no? Because Prat does very well for monophonic sounds. So you annotate the monophonic sound and then later add other instruments to make it polyphonic. But your goal is to do on Indian classical these recordings which I shared with you. They are not monophonic recordings. Yeah. So basically you don't have those audios available, but you can get some other audios to train your model. Let's say you train your model with your voice. Right? Okay, there is another actually hack, a trick to create the annotation for some polyphonic audio. Let's say you have the singer, maybe Pandit Jasraj or somebody singing, and you want to know what is the pitch contour. You don't have the monophonic audio. The trick is you yourself sing it and record it. Now this is monophonic, right? You play the audio on earphones or something, and then you start singing it, and then record just your voice. That is now only your voice, right? There is no background instruments. So this is monophonic audio, and then you can use Prat to annotate it, right? But what's the bottleneck? You can't. You can try to sing like Jasraj, but it's really difficult. Like if you try to sing like her, the singer, it's really, really difficult. Yeah.
We're training our data with
No. Monophonic is just to prepare your annotations. You can train your model on polyphonic audio, no? You have monophonic audio, you add other instruments, now it becomes polyphonic. Train your model with the polyphonic, right?
But what kind of instruments can we add? Like we can add only drone or harmonium, but not the percussion.
Why? Acha, because of. Adding other instruments.
They have to match the pitch of the main monophonic modifier. It's not similar to adding just noise to like for example in speech we add noise just
So let's say you have, let's say these tools, these tools which I'm showing, they also have instruments like tabla. So yeah. Tablas are also tuned to the tonic, the drone. Tools are there. Or for timing you can ignore that. Maybe you can ignore that. See, always, okay, attention please. So we have discussed that when you do modeling, you can make assumptions. Let's say you have some tabla sound. Okay, it does not match your tonic frequency, but maybe you can take it as an assumption, okay, let me decouple the tonic frequency from tabla frequency. Although it's not a correct assumption, but to make your task feasible, you can make that assumption. So assumptions, if they work, they are very good. All right, next. Is this clear? Any doubts here? Now coming to stroke detection. Next problem is stroke detection. This is a simple problem. Means we've already discussed at length about audio event detection. So you have to detect the stroke and the onset time of the stroke. This is the onset time. Let's say you go to this audio. Let's say here there is a stroke appearing. For stroke you have to change the spectrogram settings, right? Because you want to, it's a temporal thing. So you have to make it very short, maybe 20 milliseconds, maybe 10 milliseconds. So here there is a line and here there is a stroke also. Right, so this is a stroke. Right? Let me change the spectrogram settings and make it even smaller, 0.5, 5 milliseconds. Oh, actually, the problem is, sorry. Spectrum settings, make it full length. No, this is only 1000. Make it, because tabla will have the energy is in the higher frequencies. So make it 8000 probably. So you see here is the stroke. It's high up in the frequency, right? We were looking at the spectrogram just up to 1000 hertz. So all these things are important. So I'm doing this exercise with you so that you can get a confidence that you can do it. You can see the stroke very clearly, right? At a 5 milliseconds window. Now let's go further. Zoom out probably. See, tabla strokes are so clearly visible now. Now you see this region which had a very high density tabla stroke. But if you zoom in, everything is so clearly visible. All the strokes are so clearly visible. When you hear it seems like it's so fast, but in image you can see these strokes are visible. Right? So stroke detection means you have to detect the onset time and Okay. And you have to cluster them. Similar strokes are clustered together, different strokes are clustered separately. Let's say you have dha, it's a different kind of stroke, but tin is one kind of stroke. So cluster them separately. So how will you prepare data for this?
Sir, I've not understood what you mean by what exactly do you mean by clustering?
Clustering means I may give you an instrument, let's say tabla. You may not have trained your model on tabla. You may have trained on some other instrument or maybe something or different kind of tabla this person is playing. So I'm not asking you to find out what is thin, what is dha, etc. But at least cluster them that these all are thin, these all are dha, these all are te. That kind of clustering at least your algorithm should be able to do.
Okay, means for unknown labels, the output one output vector will be near or all the output vectors will be near some vector in some region.
Yeah. Maybe in an embedding space you can consider.
In embedding space,
Yeah,
will
like
be,
this.
at one region.
Yeah. These all are one kind of strokes, one kind of stroke, another kind of stroke, like that. All right, and there are some papers. This tutorial I think I have shared with you earlier also. This tutorial is on stroke estimation, BPM estimation, stroke detection, etc. It's a very simple tutorial. And then this is one paper on tabla stroke detection. This is a recent paper from IIT Madras, IIT Bombay group. Professor Preeti Rao is there, who works in music. And they have prepared some methods. They may be a little advanced, so don't think very complicated, right? I don't want very heavy models which are doing very complicated stuff. I want very simple things. Maybe even a simple model, maybe a simple CNN or a simple RNN or a simple dense network, not a very heavy one, just a small number of parameters, and it is giving a decent results. And focus more on understanding the concepts like signal processing, etc., rather than doing complicated models. Maybe make a model which is doing something intelligent. Like if you use CNN, why did you use CNN? Because there was some property which you wanted to use, some symmetry which you wanted to use. So I want that kind of analysis, that kind of insights from you, rather than using a model with 10 million parameters and then running for GPUs and then finally not getting good results and coming back saying, oh, our model did not do very well. But that is not the purpose of this project. Then, okay, is this clear? So what are the evaluation metrics you will use for stroke detection? Can we have attention, please? Evaluation metrics for stroke detection. Onset time, what will you do with that?
Onset time match. Like RMS similarity, closeness to the onset time.
How is too similar to caption?
Yeah. So in the audio event detection literature, we discussed several metrics like segment-based metrics and event-based metrics. So you can take help from those metrics to design metrics for this problem. Next problem is singer diarization. And we are assuming that there is no overlap. Means, okay, because if there is overlap, then it will be making a third category. So anyways, we assume that there is no overlap. There's one person sings, then second person sings, then other person sings. So first is detect the singers, detect the singing portions, and then you cluster the singers. So I'll show you the example of, okay. This is the example. So here you have, maybe I'll play the whole thing.
So the number of singers are given or not?
Okay, they are given. Let's assume number of singers is given.
Ga ga dha pa ga.
Ga ga dha pa.
Sa dha sa re ga re ga.
Sa dha sa re ga re ga ga.
So this is a synthesized audio. Basically, we have separate tracks of tanpura and tabla and the singer. We mixed them all, and we took one track from Parampreet, one track from Renuji, one track from Parampreet, one track from Renu, and then mixed them up and made this synthetic file. But the problem here is how do you kind of diarize it? Let's say I will say from here to here, singer 1 is singing, from here to here, singer 2 is singing, here to here, singer 1 again, then singer 2 again. Right? So how will you do that? Good question. Maybe we can restrict it to 2 for this project. Okay, for this project we can restrict it to 2. 2 singers. In this project, only 2 singers. So how will you do it? The first part is singing detection. You have to detect whether somebody is singing or not, right? To find out the segment. How will you do that? So first part is singing detection. How will you do that? Yeah, binary classification. That's a good idea. We can do simply a binary classification, just like you had another project, speech versus non-speech. This could be singing versus non-singing, right? And then next is singer clustering. How will you do clustering of singers? Actually, another way is that you do melody estimation, and wherever melody is non-zero, you will say something is present here. That is just another simple hack. But of course, that may not be as accurate as something else which you may make specifically for this problem. Okay, singer clustering. How will you do that? You know the regions, now you have to cluster them, whether it's singer 1 or singer 2. Let's say I give you these 4 regions and you have to cluster them now.
But can the regions overlap?
No, no overlap. We are assuming that there is no overlap.
Are we doing it as unsupervised and assuming we can either if we can assume that the windowing or the segmenting of the singers is supervised, then we can perform a clustering on some embedding like a UMAP or a TSM.
So you are doing both the problems yourself. Basically, first is the segment detection or the singing detection. Next is the clustering. So both your code is doing.
One code could handle all of the. So one code could finally generate embedding maps which could show the. If I create markers for each of the segments of the audio, then hopefully it could show what marker lies in what. All of the markers lie separately on a embedding map, and then we can say that we found 3 clusters. So 2 of them are singers and 1 is the baseline or the like unwanted part, non-singer part.
Mm-hmm.
Something like that.
Yeah.
Later on, mapping the cluster to the singer would be a different problem. That would need labels, but till here we don't need any labels as such. We would be clustering them based on audio properties itself.
Right. Yes. Even your singer clustering can also be done based on audio properties now. Let's say your voice and my voice. How are they different? What are the features which will distinguish?
We create a feature vector, and based on that feature vector, we could cluster them.
Yeah. So what feature vector will you use?
We could intensity, formants, frequency. I will have to look into literature on how speakers.
But if you look at formants, when I say different vowels, they have different formants. So not different speaker. Same speaker but different formants. Right?
Maybe we look into something which differentiates people. I mean, what some literature will be called decide feature.
So very quickly I will tell how people do it in literature. I don't have my iPad here, so I will just write it down here. So since it is a what do you say, it's a mixed audio, polyphonic audio. So first you may try to extract the spectrum of the singer alone, means without any interference from other instruments. So how do you do that? You use something called a harmonic comb filter. So what, let's say I have my spectrograms or the magnitude spectrograms. Let's say I have my x, m comma k. This is spectrogram, right? I will multiply it with a filter, and this is a element wise multiplication. I'm not taking dot product, it's just element wise multiplication with a filter which is a harmonic filter h, m comma k, and it is a harmonic filter at a particular pitch p, which means this harmonic filter has got peaks at the pitch p or the f0, 2f0, 3f0, 4f0, 5f0, etc. So it's like just a comb kind of structure, right? There is a peak at f0, peak at 2f0, peak at 3f0, and in between you have very low amplitude, maybe 0 or very low amplitudes, right? So now when you multiply the two, what will happen? So this is a singer plus some noise. This is my comb filter. When you multiply them, only singer thing will come out. Everything else will be reduced to 0 or very low amplitudes, right? So in this way, first this is a very simple kind of source separation, right? This is the simplest kind of source separation you can think of, where you know the pitch of the singer and you just multiply it with a comb filter of that same pitch. Then you're able to separate the singer. Now you got this filtered thing. Let me call it as x underscore p m comma k, right? Now you can treat this as your spectrum and then and extract features from here. What features can you extract? You can extract features like MFCC, or you can extract log filter bank energies, right? All these things we have discussed in the past. Yeah, it can't. If you have multiple people singing the same pitch, then it's difficult to separate, no?
There's also a condition that both the singers sing in different pitches, right?
No, they don't sing simultaneously, no? Both singers are not singing simultaneously in this problem.
But still, how is separating if two singers sing in the same pitch?
That problem will not come in your project. In this project, that problem won't come. Only drone is interfering. So you're just reducing the drone part.
So in the audio which you just played, the two singers actually sing the same thing again, right?
Uh-huh.
So then how is exactly separated?
But they are not overlapping, no? They are one after the other. This is for overlapping, like within the same time frame. If two things are occurring, then you want to separate one of them, then you can separate based on pitch.
So if we have a certain data set in which we have multiples, for example, it is just like a cocktail party. If we have multiple speakers and multiple receivers, we can do some ICA based decomposition of the audio.
Yeah, there are more sophisticated methods to do that, like ICA, and then even more sophisticated like non-negative matrix factorization, etc. people use. But then they are based on the premise that either you know about those speakers beforehand, or in that audio itself they're not overlapping all the time. There are significant number of times when they are not overlapping, their pitches are not overlapping, and then you use that portion to learn about their characteristics and use them for the regions where they're overlapping. So and let's keep it simple, means we will not go into that overlapping thing at all. So this is simple kind of source separation, and then from this spectrum you can extract features like MFCCs, etc. And then what you do next is you can do a clustering now. In this MFCC's feature space, let me call this as C underscore I. Okay. No. So what I do is, now see here, Oops. Please pay attention here. Don't do cross talking. If I extract MFCC from only single frame, let's say I'm saying A and I only say E, then these two MFCCs will be so different. You can't make out whether it is speaker is same or not. So what generally people do is they extract these features and then they average over the entire segment. Let's say I'm speaking. So you average it out basically so with the assumption that let's say this is the region. In this region, my speech lies and my A, E, A, U, everything lies here. And if somebody else speaks, that person lies in some other region, A, E, I, U. And then when you take the average, then this centroid and this centroid, they are still separated. That is the basic assumption to use this kind of an average over the segment. Basically, average features over the segment. Right? Are there any problems? Is it fine? Can you use this algorithm for your task? Can you use this for your task? Can you use this for your task?
So I want to confirm one thing. So are you saying that first we have to detect the speech speech segments, the segments where speech is present or not, and then in those features in those segments we have to like calculate the MFCC, and in those segments the MFCC contour will be very similar.
Yeah.
In those segments for that individual segment.
It is not similar. Means you average it up and make one feature, and you can assume that is a centroid for this speaker. Another speaker, when you average it up, it is a centroid for this speaker. And then you can distinguish between these two centroids. That is this method. But there are flaws or limitations of this method also. What is the limitation? One limitation is that
The segments are very different for one segment. And since we are taking the average of the segment, if in two segments the singer is singing very different things, so they won't be
no, but when you take average, you will get the middle point, that is the centroid. What is the problem? The problem is that in music, people generally sing single vowel. Then they stop. So one whole segment is just one vowel. It is not multiple vowels which you can average over. So that's why in music this may not work. I have not tested it. You can test it. It may not work. So another method is, first you do vowel estimation and then you do distinction. Let's say I said what's your name? Apurv. Apurv said If you know I said so okay, look at my look at Apurv's and then distinguish between the two. And whenever say Apurv says E, don't compare it with my compare it with my E only. I said E, Apurv said and E. Compare his E to my E, his to my and based on that you try to distinguish the two, right? So that is the other approach, that you first detect the phoneme, which phoneme it is, and then based on that phoneme you distinguish. Now again the problem, okay, even this model has a problem in this model has a problem for our current problem, statement. What is that problem? This is a limitation, I would say. So this is phoneme based clustering, another method. What else? So what is the limitation of this method?
You don't need the phonemes for every speaker individually.
Yeah. You may not have phonemes for different singers. Let's say I am singing only and Apurv is singing E only. So you may not have the phonemes. So what will you do? What is the remedy for this problem? What will you do then? What will you do then? Phonemes are not available. I never sang an E. I only sang A. And Apurv never sang an A. He only sang E. Okay, homework. You will get this question in the exam. Okay, let me answer. I don't want to keep you kind of confused. So what you can do is do training. Let's say I know Sanreet. How he says a. If he says a like this, then his E is like this. What's your name? Mudit. If Mudit says a like this, he says E like this. What's your name? Shrey. If Shrey says a like this, his E is like this. Lalit says a like this, his E. Now you can kind of estimate, if I am saying a, I never said E, but my E will be like this. And you know Apur's E, compare them.
Then we need another model for this.
No. You try to make a model which is speaker independent, basically which take any a and try to estimate the E. But you don't make this model literally. Your model learns, let's say Sanreet's space is like this. Whenever he says a, it is here, E is here, etc., etc. And then this model tries to learn features in such a way that,
The invariant of the.
yeah, kind of invariant of the speaker, something of that sort.
Basically, it should generate all the phonemes.
For any,
For any speaker, it should generate all the phonemes.
yeah. Or in other words, it may be speaker dependent but phoneme invariant. Means if I hear Sanreet's voice, it could be a or E, whatever, but I map it to the same region. Now if I say Mudit's a or E, whatever phoneme it is, I map it to the same region. So something of that sort, right?
So wouldn't if we can choose features which are lyrical invariants, then it wouldn't be better for this problem.
Lyrical invariant.
Phoneme invariant. For a person, for you, if you sing, those set of features always remain close to each other.
Yeah.
So that would be the.
Yes, ideally that could solve the problem in one shot.
So if we can find those features or experiment in generating those features.
Yes. Yeah, there are many works available on speaker diarization which try to do that, which try to learn such models. So you can work with them. Okay, thank you very much. So we stop here.